Hello Science Alliance, hello my IGCSEs, I am Lara. This is Theatre of Science. I stream free live lessons for home educators, and I like this one because usually I wear a silly costume and teach you about whatever you're making me teach you, like centaurs if you're watching my all ages lessons live this week. But I am actually trained to teach physics up to A level, so let's do that. Let's learn some physics. You have come to the very first astrophysics module of this sort of course. I'm just doing the whole of IGCSE physics live into the internet. Oh, this is a really good time to join in. So while I'm chatting, can you please, just to get started, I said to bring a can of food. I've been quite rude, I've already done it. While I'm talking, can you cut out a little bit of paper and write an N on it? And cut out a little bit of paper and write an S on it and stick it on your can. I thought we wouldn't all have like balls, footballs, tennis balls or whatever lying around the house, but I thought you'll all have a can of food. So we'll pretend that this is the Earth, okay? And we'll just do a really simple little model to get a feel for what Earth is doing in relation to the moon and the sun. Okay, can you do that? Usually I do the activity with you. It feels rude that I got ahead of you because this is yesterday's, but that's all right, yeah? I mean, you could just write an N and an S on a can if you want, but that's cheating and not as crafty. Okay, so there's two exam boards who write an IGCSE physics exam. There's Cambridge and there's Pearson EdXL. So you probably don't know. You might not even be planning to sit IGCSE physics. You might just be here for fun. But if you end up taking an exam, it'll either be written by Cambridge or Pearson EdXL, and it's really important you know before you go in which one to revise because they need you to know slightly different things. Most of the stuff they need you to know is exactly the same. Like pretty much throughout the whole of this course, waves we've done, forces, it's all saved on my website. It's just been the same stuff and I've just taught you it all the same. Cambridge get really excited about astrophysics. There's loads of stuff that the Cambridge exam might need you to know about that EdXL Pearson just aren't bothered about. So we'll quickly mention the seasons right at the start of this lesson now, but that's only on the Cambridge specification, and they might want you to know about the moon's phases as well, which we won't talk about today. I don't usually do that, but yeah, because it's so much content and it's only on one exam paper. We'll leave it be. I think the only other thing that you need to know before we get started is we did this in the forces module. Are you okay with the fact that gravity pulls things, we'll say gravity pulls things towards the ground, and the more massive something is, the more gravity something has. So everything has mass, right? Mass is just how much stuff a thing is made of, okay? How many particles a thing is made of. So Earth has got a lot of mass. It's massive. It's made of loads of particles. So the force of Earth's gravity is sort of pulling you down towards Earth, we'll say. The moon, it's still really massive, but it's slightly less massive than Earth. So you probably know that you can do big jumps on the moon that you can't do on Earth because the moon isn't pulling on you as much because gravity is weaker on the moon because the moon has less mass. Yeah? Sun, very, very, very massive, huge amount of gravity. Yeah, I think that's the only thing you sort of need to know that we discussed previously. Okay, have you got your can of food that is now being turned into an Earth because it's got a north and a south pole, yeah? You can imagine, if you like, that your finger is the moon and the can is the Earth. Let's say that your head is the sun. How much do you know about what is happening here, about how each thing works? So you might have sketched this at the start of the lesson. You might have sketched that the moon goes round Earth, and that is correct. Well done. And if you sort of drew it as like just a circle around Earth, that's pretty good. Yeah, the moon's orbit, in fact, most moon's orbits are pretty much circles, like roughly circular. We'll talk more about that in a bit. If I do my planet Earth orbiting around my sun head like that, is that okay? Is that okay? Anything that you would improve on there? Couple of things you could improve on. One of the things is Earth is tilted, isn't it? Did you get that? If you drew a sketch, did you get that Earth is tilted? This is super important for the seasons. So if Earth wasn't tilted, the middle of the planet would just be hot all the time and the poles would be very, very cold all the time. That is not the case. How the seasons work, very briefly, is that the Earth is always tilted at a constant angle. It's 23 degrees, I don't think you need to know that. But when the North Pole is pointing towards the sun, it is summer in the North Pole and winter at the South Pole. It's snowing in the UK where I am on the north of the planet, because the planet is roughly positioned like this. So at the moment, if you're watching live with me in end of November, the north of the planet is pointing almost as far away as it ever gets from sun. So the seasons aren't about how far Earth is away from the sun, it's about this tilt. So at the moment, the south of the planet is about to get its summertime and the north is heading in for deep winter. All right, I'll put it on a PowerPoint, because the other thing is, this sort of seems simple, but I think it gets confusing because the way that we use language in everyday life is very different to how it actually works. Like, we talk about the sun rising and setting, yeah, don't we? No one ever says anything other than the sun rises and the sun sets. But that's not actually what is happening. If you imagine that I am on these little, imagine that one of these little green circles on my can is a human. What's happening when a day goes by is not that the sun is like moving across the sky, it's that Earth is turning. So at the moment, these little green people are in full daylight, and as Earth turns, they start to lose sight of the sun. The sun's going away. It's like dipped behind the horizon, and now the sun has disappeared. They can't see the sun anymore. So the little humans are like, oh, the sun has gone. And then they come back around again, and then they start to just glimpse the sun, and that would be the sunrise. And eventually the sun comes up. But actually, I mean, the sun is moving, but it's not going up and down. That's not what is happening in a day. I did this on a PowerPoint for your viewing pleasure. Here we go. This is how I have to do it to understand it. Earth is tilted. When the North Pole is tilted towards the sun, it never sets in the north. So let's imagine a little person stood really high up on the North Pole. You might have heard this thing about like the sun not setting at the North Pole or the North Pole being plunged into darkness. This is why that happens. I need a pointy thing. Here we go. Imagine a person on the North Pole in one whole day. So they're standing in the same place on the planet, but the planet is moving around like we just did. They go whoop and whoop. So they've rotated around one whole rotation in one day. But as you can see, the sun has never set for them. They've just had daylight. They've gone to bed in daylight. They've woken up in daylight. Let's put another person just a little bit further down. What happens to them? They go around. In one day they come back. It's still just constant daylight. Let's put person quite a bit further down. Can you see that they have now gone far enough around that they get just a very short amount of nighttime, and then they come back. So that's why we say that we have like long days in the summer. Whereas if you were stood at the South Pole, which not many people are, not as many people live down there, so why we don't talk about it as much, that person would be getting night all of the time. Okay? Phew! So that's all we're going to say about the seasons. And like I say, you also need to know how the moon's phases work if you're doing the Cambridge exam. But we're not going to do that today. We're going to move on to a delicious equation, which looks hard, but actually it isn't all that complicated once you really think about it. So let's have a think about it. We're going to talk about orbital speed. Speed, how fast things travel. So we will improve this model a little bit more by the end of the lesson, but we're going to talk about how you can work out how fast something is orbiting something else, okay? And the equation for it is 2 times pi times orbital radius divided by time period equals orbital speed. Let's break it down, okay? Some of you will know this and some of you won't, so I'm going to start from the beginning. The radius of a circle is the distance from the centre of the circle to the edge. Yeah, a lot of you might have known that, some of you might have not. That's the radius of a circle, that bit there. Some of you will know this as well. 2 times pi times r, for what we're going to call magical reasons, equals the circumference of a circle. So if you want to measure how, what would you call it? How long? If you want to measure the distance, there's a reason we have the word circumference, isn't there? It's the easiest one to use. If you want to measure the circumference of a circle, this distance here, you do 2 times pi, which for today we're just going to say is a magic button on your calculator, times the radius, and that gives you the circumference. That's pretty cool, eh? So the orbital radius is just the distance from the centre of whatever the thing is in the centre, let's say it's the sun, to the centre of Earth. And that's it. That's the orbital radius, because it makes sense, doesn't it? So how do you work out how far Earth is travelling around the sun, the distance that Earth travels? Well, I mean, it's not a circle, which we'll look at the end of the lesson, but you can say it's 2 times pi times that orbital radius. So then you get the distance. It's just the circumference of a circle. Phew! So 2 times pi times orbital radius. That's just the distance that the thing that's orbiting travels. The orbital speed is just posh astrophysics talk for speed. So how fast Earth is going is the distance it travels, 2 times pi times orbital radius, divided by the time period. What do you think time period is? What does time period mean? Oh, if you came to our forces lessons, or if you've done even just a little bit of physics before, you might have spotted quite a simple equation which physicists talk about a lot. It's just speed equals distance divided by time, isn't it? The time period is how long it takes Earth to go around the sun. Woohoo! Right. Okay, so have you been paying any attention? Very quickly, because if you haven't picked this up, we can't go any further, right? Which of these pictures shows an orbital radius, please? You've got 4 pictures of the sun with a little smiley Earth going around it. Which one of these shows the orbital radius? Is it A, a line going from the centre of Earth to the edge of the sun? Is it B, a line going from the centre of Earth to the centre of the sun? Is it C, a line going from the far end of the Earth to the far end of the sun? Or is it D, a line going from the edge of Earth to the centre of the sun? I'm just going to show you the answer because you probably either know it or you don't know it and you want me to tell you. The answer is, it's B. Yes, the orbital radius is the distance from the centre of the thing in the middle to the centre of the thing on the outside, okay? Another question. Oh, I'm so happy with this question. Which of these could be an orbital time period? Which of these could be an orbital time period? A, 30,000 metres per second. B, 30,000 metres. C, 30,000 kilometres per second. D, 30,000 metres. I'm pleased with this because I could have just said to you, what does orbital time period mean? But I think this is more interesting and more the sort of tricksy thing that an IGCSE physics exam would ask you. Which of these could be an orbital time period? The answer is, again, I guess it helped if you did forces and you know about units. So if something's measured in metres per second, that means it's a speed. So this is a speed here. It could be an orbital speed, but it can't be an orbital time period. Kilometres per second, that would also be a speed. How many kilometres something is travelling per second. Metres is how you measure distance, so you can't measure time in metres. So it's got to be the seconds, and it is. Yeah, it was B. Right. Phew. This question, when I taught this, so I've sort of already taught this whole IGCSE course once before, and now I'm teaching it again with a slightly updated specification. I put this on as a big full question last time. I'm not going to do that this time, but I'll give you like a couple of seconds just to look at it, and then I'll show you the answer. I wanted you, when I did this lesson ages ago, to put the terms on the right onto the diagram. So like, where does meters per second go? Where does meters go? We're not going to bother, but if you were given all this information, can you spot something you'd have to change before you did any calculations? Here you go. So again, you've got, not to scale, you've got Earth going around the sun, and I've told you that that takes roughly 365 days. And you could be thinking about which of these gets matched up with which of these units. Where would you put the 2 pi r? That sort of thing. Thanks for all the likes, by the way. Loving the amount of likes on this video. That's very kind of you. All right, yeah, I'm just going to do it. I feel like it'll be more useful for us to just go through it together and then we'll get to a question. So, orbital speed is just how fast the thing that's orbiting is going. We'll say Earth and Sun because it makes it easier. How fast the Sun is going around Earth is its orbital speed, and that is measured in meters per second. You've got to be so careful with the units in questions like this. Physicists use meters per second to measure speed. If you see anything different, you'll have to change it into meters per second. The orbital radius is measured in meters because that is a distance. And the orbital period is how long it takes for, say, Earth to go around the Sun, and that's 365 days. The velocity, that's like the speed, basically, orbital speed. And 2 pi r is this distance here. 2 times pi times the orbital radius is this dotted line, the circumference, if you like, the distance that Earth is travelling. The thing that you would have to change if you wanted to do any calculations is days, because you've got to make sure all your units are the same. And if you're talking about meters and seconds, you can't put seconds into an equation with days. That's not going to work. You need to change days into seconds. Right, okay, have a little look at this. I'm quite pleased with the questions in this lesson. So some of you will be at a really high level of maths already, done loads of maths practice. Some of you will just be thinking, I'll try some IGCSE physics, but you haven't done any maths before. So what I'm going to do is, you can do the maths in the questions, but also I've designed the maths questions to be more about thinking as well, because that's what an IGCSE physics exam will do. They'll be throwing in like little extra bits that you have to work out to check your understanding, not just check your maths. So I'm doing that here. So the International Space Station, right? You know, the International Space Station, the spaceship that's just orbiting Earth right now in space with humans on it. It orbits Earth at 400 kilometres above the surface of Earth. It takes 5,400 seconds to complete one orbit. If I ask you what is the orbital speed of the International Space Station, can you work it out? Or do you need any more information to answer the question? Or if you can do it, just do it now, please. The ISS is orbiting Earth 400 kilometres above the surface of Earth. Takes 5,400 seconds to complete one orbit. Can you work out its orbital speed? So the answer is no, you can't calculate it, can you? Yes, you do need some more information to answer the question. What do you need? Well, you've got the time period, you've got how long it takes to complete one orbit, that's 5,400 seconds. I even put it in seconds for you, that was kind. You're looking for the speed, pi is just a number, 2 is just a number. You haven't got the orbital radius though, have you? I haven't given you the orbital radius. I've only given you the distance from the International Space Station to the surface of Earth. So the extra bit of information you need is what's the radius of Earth? And then you can add that on. And then you've got the orbital radius. We're not going to worry too much about the width of the ISS because it's so small, we don't really have to worry about it. So Earth's radius is 6,000 kilometres. Now have you got the information that you need? You've got to do something else, haven't you? Before you just stick these numbers in, you've got to do something else. What do you need to do? Do you remember us saying about meters and seconds? We need to change those distances into meters, really. I mean, we could leave them as they are, and then our speed would be in kilometers per second. But let's change them into meters and get our speed in meters per second. So there's 1,000 meters in 1 kilometer. So if it's 400 kilometers and you want to know how many meters it is, you've got to change it by 1,000. You can learn this maths later, you don't need me for this, but we'll say that 400 kilometres is 400,000 metres, because it is. And Earth's radius then is 6,000 kilometres, which is 6 million metres. So let's add all that together and we've got our distance. Our orbital radius is 6,400,000 metres. Phew, now we've got everything we need. Okay, so the answer is, if you put that in your calculator, which I will give you a second to do, because you might want to do some bracketing or you might want to press equals before you divide it. Can you get the answer? 7,446.7. I'll do it with you. 2 times. Are you okay finding pi on your calculator? If you haven't got a scientific calculator, you're not going to be able to do this, really. But my pi is hiding down here. Can you see it's in yellow, which means I need to press this little shift button before it'll give me pi. So if I press shift, boop, and then I press that, oh, there it is, great. I'll point you at the screen again, sorry, that's probably really annoying. Have you got it? If you are doing an IGCSE physics exam, you'll have to learn about things called significant figures as well. But we won't go into that here. But if you want to look up significant figures, or you know about them, and you want to make sure that your answer is in the right amount of significant figures, That would be cool. So I suppose technically that would be 7,400. Right, can we move on? Oh yeah, meters per second. So I love this about units. Whatever you do to the numbers, you just do to the units. So if you're dividing meters by seconds, the answer is meters divided by seconds, like meters per second, right? And that's a good sign that you're on the right track, because you know that speed is measured in meters per second. Okay, can I give you a nice meaty question to do? If you like things to do with your hands, then while you're doing this question, what you could be doing is folding up a bit of paper into just you don't have to fold it a precise amount of times. What you need is just a blob of paper on the end of a string, okay? Because we're just going to swirl it around and have a little chat about orbits at the end. Do you get me? So fold up a bit of paper just into just a kind of blob of paper, a chunk of paper, and then tie some wool around it to make something on a string. If you like something to do with your hands, or you can just focus on this question. This is my big, how much have you understood? Orbital speed question. There's loads of information here. Again, I'm really chuffed with this. I think this is sneaky. Some of this info you need and some of it you don't need. So if you don't do the maths, but you manage to work out what information you need, I'll be very pleased with that. Mars has a radius of 3,400 kilometres and is orbiting the Sun with an average orbital speed of 24,000 metres per second. Okay? Mars is going around the Sun at a speed of 24,000 metres per second. And Mars has a radius, as shown here, of 3,400 kilometres. The United Arab Emirates HOPE probe has been in orbit around Mars for 4.5 years. If you have the printout, I'm really sorry, I forgot to update it. You've got the date, you've got the number from 2 years ago. I updated it on the PowerPoint because it's still going. The HOPE probe has been in orbit around Mars for 4.5 years. It orbits Mars at an average distance of 30,000 kilometres and takes 20,000 seconds to complete one orbit. What is the orbital speed of the HOPE probe? I've tried to make it loads more complicated than it should be. I could have simplified it, but I've made it complicated on purpose, because the first thing I want you to do is to spot which one of these many numbers is the time period. So you're looking for the orbital speed of the HOPE probe. So you need an orbital radius and you need a time period, but you need to pick the right ones. So write down the time period, calculate the orbital radius, check your units, and then if you get that far, you can do the calculation as well. If you really don't get it, and you just end up staring at the screen blankly for 30 seconds, then, sorry, that is really annoying, isn't it? It is still doing your brain some good. Like, you're still fusing neurons. If you just stare at this getting angrier and angrier, I mean, it's not good. It's not like the best way to learn. But it does mean that when I give you the answer, you'll get more out of it than if I just showed you the answer in the first place, if you see what I mean. So if you don't get it at all, well, if you don't get it at all, the best thing to do is to draw a diagram, actually, isn't it? You've got Mars, and the HOPE probe is going around Mars, okay? So I want you to work out how fast the HOPE probe is going. Its average speed. It's just its speed, but we've said orbital speed because the HOPE probe is orbiting Mars. So the HOPE probe is orbiting Mars, going around Mars. So to work out how fast it's going, you need to know how long it takes to get all the way around Mars. And you also need to know the orbital radius, the distance between the centre of Mars and the HOPE probe. And all that information is on here, but with an awful lot more as well. I should say, if you're watching live, then you'll have noticed there aren't any comments on this video. But whenever I'm live, I always put up a Facebook post on my Facebook page saying, you can comment on this post and then I'll say hi to you at the end. So if you've got a Facebook account and you want to go over there right now and comment, then I will say hi to you at the end. If you haven't got a Facebook account, then that's the right answer, isn't it? No one needs a Facebook account. So well done, you. I see you lurking. I know you're watching and I'm very grateful, so don't worry about it. You can always message me, can't you? If you really want, you can email me to say hello and I can email you back. Or you could just imagine that we've said hi. Should we go through some stuff? Should we look at how we calculate the orbital radius? So the orbital radius is the distance between the centre of Mars to the centre of the Hope probe. Hope probe is very small, so we're not going to worry too much about that. I gave you the radius of Mars, 3,400 kilometres. And I gave you the distance that the Hope probe was above the surface of Mars. But that would just be the kind of mean trick that they try and pull on you. So make sure that you've got the right distance. So you need to add those together. And the orbital radius is 33,400 kilometres. Which, if we times that by 1,000, we get 33,400,000 metres. Okay, so that's the orbital radius. The time period, we need the time period, how long it is taking this Hope probe to go around. So the time period is how long it takes, to complete one orbit. So it was 200,000 seconds. I put it in seconds for you. So yeah, sorry, all this 4.5 years thing was just a bit of a cheat really to try and confuse you. Okay, so we need to check our units. Are our units okay? We've got 2, pi, they don't have any units, they're just numbers. We've got meters, we've got seconds. Woohoo! It's looking good, chums. Okay, we can work it out. I'm not going to put the answer on the board. Let's see what you get. I'll do the same. 2 times pi. Stop talking out loud, Laura. That's not helping anyone. And I get the answer 1,049 metres per second. Whew. Is that what you got as well? 1,049 metres per second. That's how fast the Hope probe is going. It's very much its average speed. We'll talk about that in a sec. Okay, can we crack on with talking about shapes? Because I was really hoping that some of you would have at least got some of these shapes incorrect, which would give my life purpose, because I get to teach you about shapes. So if you didn't do it already because you were doing awesome maths, can you please tie a bit of paper to the end of a bit of string for reasons, just for helping, for learning. And while I'm telling you about shapes, if you're doing that, then in the end, we'll talk about something really nice that really blends energy, which we just looked at with this topic today. Okay, what shape is this? I asked you, and I showed you 3 different shapes. This one in the middle, this is just, if you said egg, then yeah, it is an egg. We will not concern ourselves with this today. Sadly, there are very few eggs in astrophysics, so we're not going to talk about that. If you said that this top one is an oval, you're right. Technically, all of these shapes are ovals. An oval is just a very unmathematical, unprecise word for a sort of an egg shape, squashed circle type thing. So even though I've just said it 12 times, you must not speak of ovals if you're doing astrophysics. Forget the word oval. Don't even think about it. Stop thinking about the word oval. The word that you need is ellipse. This thing is an ellipse. An ellipse is basically a posh mathematical oval with a precise definition. So we don't really need to go into the definition, but an ellipse has 2 focal points, one on either side of the centre and equidistant from the centre, so it's symmetrical, okay? Yeah, that's basically what an ellipse is. So a circle is, it's kind of a fancy ellipse where both the focal points are sort of together in the middle. But yeah, it's a mathematical shape with a mathematical definition, and a lot of planets orbit stars in this elliptical shape, which is why we're talking about it. And yeah, that's a circle. Well done. It's also a special kind of ellipse. Okay, so the planets orbit around the sun are elliptical. We're going to do more about the planets next week. But the planets in our solar system orbit our sun not in a circular move, but in an elliptical move. So maybe some of you have learned something there. If you were doing this with your can, and then I said, oh, don't forget you've got to tilt it. Even if you were doing this, technically we can improve that model now because this should be an ellipse. But this diagram that I'm showing you is still wrong. Even though the orbits of the planets are shown as ellipses in this it's not a diagram, is it? Picture. A mistake has been made. What could that mistake possibly be? I'm going to give you milliseconds to think about it while I attempt to draw an ellipse on the board. It always ends up as an egg or a circle. Oh, it could be worse. It could be worse. Do a little E for Earth. So the answer is, this is wrong because the reality is the sun is at one focus. It's not in the centre, okay? So it's not my worst ellipse. The temptation would be, because, you know, we always do this, don't we? This is just not, humans love talking about space more than they love learning about space. So people always get this wrong. The sun isn't right in the middle of the ellipse. It's at one focus. So let's put it over here. Okay. And yeah, one of the things that you have to know is the difference between the orbit of a moon and a planet and a comet. We'll talk about comets later, but the big difference between a planet and a moon is that the moon's orbit is more or less circular. Our moon's orbit is actually really complicated because it doesn't know whether it should be obeying the sun or Earth. It doesn't know who's pulling on it more. But Earth's orbit is very much elliptical like this. Right. Have you got your bit of stuff on the end of a piece of string? If you have, we're going to finish the lesson by talking about energy. If you've been to my energy lessons, like we just sort of finished talking about energy, we've got a bit about generating electricity to go, but we basically wrapped up the energy module last term. If you've already done that, this will be like, oh wow, cool, interesting. If you haven't done that, this might be a bit annoying, but stick with it, and then you can always watch it on catch up on my website, or you can just stick with this learning, and then in 2 years' time we'll learn about energy, and you'll be like, yeah, cool. So we were talking in our energy lessons about gravitational potential energy. That just means that something has the potential to fall. If you lift something up, like lift up your little bit of paper, you've given it the potential to fall. So when you let go on, let go, it falls. So as it falls, you could say that it's losing, we used better language in the energy lessons, but I'll keep it simple. You could say it's losing gravitational potential energy. It's got less potential to fall because it's getting lower. But we learned that energy can't be created and it can't be destroyed. Energy can't just disappear. So this thing's losing gravitational potential energy, but it's gaining a different kind of energy. It's gaining movement energy. So as something falls, it loses the potential to fall, it loses gravitational potential energy, but it gains movement energy. And we looked at, wow, that was a very poor notch. We looked at, well, I've got it from yesterday. It's fine, it's okay. I've got it from, here it is. I'll just use yesterday's. We looked at this in our energy lessons. We looked at sort of how a swing works and was saying that the swing's got most gravitational potential energy here, but it's actually going the fastest at the bottom because it's got 0 gravitational potential energy and 100% movement energy. So it goes, speeds up, speeds up, speeds up, as fast as it can get, slows down a bit, slows down a bit, slows down, sort of basically just stops at one far end as it's changing direction, and then does the same thing. Speeds up, speeds up, speeds up, speeds up, as fast as it'll go, slows down, slows down, slows down, stops for a minute, not a minute, but stops, speeds up, you see what I mean? Like that. What you need to know about orbits is that when a planet, let's say Earth, when Earth gets close to the sun, it speeds up. And it's because of this, how we've talked about energy when we're talking about a swing. what Earth is doing, what all things that are orbiting things are doing, are basically falling. So Earth is falling towards the sun, but luckily for us, it keeps missing. That's what orbiting is. It's just trapped in the sun's gravitational field in exactly the right position so that it misses the sun every time it falls towards it. But yeah, it's falling. So when Earth's over here, it's got as much gravitational potential energy as it can possibly get, right? It's got a long way to fall. So just like this, it falls towards the sun. It falls and falls and falls. It loses gravitational potential energy until it gets here, as close to the sun as it can get. And it's got very little gravitational potential energy, but it's got the most kinetic, the most movement energy it ever gets. So it's going fast. Does that make sense? Because at first it sort of seems like not very intuitive, like you wouldn't be able to work out when is it fastest and when is it slowest. But yeah, that's how it works. There, lots of gravitational potential energy. There, lots of movement energy. Going fast. It's good, isn't it? It's good. So yes, hopefully with that, we've covered the whole very beginning bit of all the things that you need to know if you're doing EdXL specification. And if you're doing Cambridge, you just need to go away and learn about the moon's phases. The only other thing that I'll say, just before we go, let's do another little practical. If you're pinching your bit of string between your thumb and your finger, okay, can you make the piece of paper orbit your thumb and your finger? Do it, please. Do it right now. Make your bit of paper orbit your fingers. So one thing to say is that the more gravity a planet has, excuse my poor physics language, but the more gravity something has, like the more massive a star is, the faster the thing can go around it. Sort of in a similar way to the more you pull on this bit of paper, the faster it goes around. Can you please, just before we finish, can you make this paper spin around without moving your finger and your thumb? Can you get it that your finger and your thumb stay still? Because you'll notice, like how I'm doing it now, my finger and my thumb are moving in a little circle. So can you make it that your finger and the thumb are staying exactly still, but the paper is going around? You got that? Can you do it? Not moving at all. Have you done it? Have you worked out how to do it? You can't do it, can you? You can't do it. It's impossible to do it. You need to be pulling on the string, but Newton's laws, which we've already discussed, mean that the paper is sort of pulling back on you, and it's the same with this setup here. The sun is not completely still with Earth going around it. In fact, the sun is, just like your hands were, the sun is moving in its own little circle as well. So the centre of mass, if you like, of this situation is not the very centre of the sun. Whew. And on that note, I will finish there and go over to my Facebook page and see if any of you have left me any comments. If you haven't got a Facebook account and you find this a bit tedious, then don't worry about it. That was my lesson. Thank you so much for joining me. I will very quickly tell you how I teach these lessons for free, because it's this really weird business model that I just made up by accident in lockdown, and it's working ridiculously well, and I need to tell everybody about it. So what happened was, started streaming free lessons in lockdown. Home educators, it turns out they were watching and they wanted me to keep going. Obviously I wanted to keep going, best job ever, look at me. So I just said, okay, there's this website called Coffee where you can sign up to support people like podcasts and stuff. So I set up a Coffee page and I said, if you want to send me £5 a month, that'll be enough for me to keep going. And you just are. It's so cool. Like, everyone is really grateful. So you're really grateful because I'm just doing everything for free. Like, I've got a first-class drama degree and a first-class science degree, and I'm a fully qualified secondary school teacher, and literally all I do now for my job is stream lessons like this into the internet. I don't do any one-to-one tuition. I don't do any sort of private Zoom classes. You are my students, and yeah, just say it's free for everyone. The printouts are free, they're optional, you don't need them, but they're free. Everything's stored on my website for watching on catch up. Lessons are free, it's all free, and I just say, pay me if you can. Yeah, and you are. So you're grateful for that. I'm super grateful because look at me, this is so much better than teaching in a school for so many reasons. Also, like, it's just so much easier for me admin-wise if everything's free. And yeah, like, it can be free, because you're choosing to pay me. So it's thanks to you that it is free, if you know what I mean. Like, I'm not, people always like, oh, thank you so much. I'm like, I'm not doing it to be kind. If I wasn't making any money, I wouldn't be able to do it. But you're all sending me money. So yeah. If you want to support me, if you're like, yeah, this is useful, I'm using her as a resource, then you can send me £5 a month on this website called Coffee. Go to my About section and click the sign up button. It's like, there's a link to Coffee in my About section on YouTube. Or you can go to my website and the sign up button is hopefully all over the place. Or on YouTube, Facebook, it's there as well. But yeah, if you sign up, I send you nice things to say thank you. So if you sign up at the moment with £5 a month, you get Theatre of Science magazine, past issue, which is about mould. I'm always writing Theatre of Science magazine. It hardly ever comes out, but I'm always writing it. It just takes me ages. So if you sign up, you'll be on the list to get the next one. But I'll send you this past issue to keep you going. It's got a home compostable plastic bag. You make this tray, you put food in it, you put it all in a plastic bag, you grow mould on the food. So good. I should do it again. And then you can just compost the whole thing at home. It took me ages to find a bag like that would just break down in the ground. It's got a beautiful comic that my husband illustrated for me about the discovery of penicillin. It's got a load of stuff about how mould works. It's got choose your own adventure. And if you're watching live, if you sign up at the moment with £6 a month, you get that, and you get the pine trees issue as well. I've called it the Christmas tree issue. You don't need to celebrate Christmas. It's just about pine trees. It's got like a pine tree spotting guide. So if you're in B&Q in the next couple of weeks, or your local independent garden centre, you can have a look at the tree, answer various questions, and it should be able to tell you, because I spent a long time on it, whether you're looking at a spruce or a fir or a pine tree, or maybe even a deciduous conifer. It's got some pine tree bunting on it, which gives you little facts about pine trees. I think this is my favourite one. It's got a comic about the First World War and the truths that happened that I can't tell you about because I will cry. And I'll send you some, well, I call them rainbow glasses. You're IGCSE physicists, so I can tell you that they are actually diffraction glasses. They make see rainbows though, they're very cool. And I send you a description of how they work, which I never mention, but it's the most important bit. For you, it's just a whole bit of information about diffraction, which would be useful. Okay, that is the end of my ad. That was a lot, wasn't it? So much talking. Let's have a look at these Facebook comments. Oh no, Thomas and Isabel, what are you saying? Hi from, someone's put, no, oh, oh no. Okay, right, I've made you realise you have no kidney beans for your chilli tonight. Oh, it's always the way. That's the one thing that always stops me from making chilli. It's the blooming kidney beans. I don't use them for anything else. Hello, Jacob. Hello, Freya and Hannah. Hannah would like to share her unicorn again. Oh, thank you, from last week's lesson. Oh, that's brilliant. Good, because my battery died, didn't it? Hello, Bastian. Yellow from Miles. P.S. I'm 8. You're 8? Miles, I'm trying to remember. You've said yellow, like yellow. Oh, wait. Is yellow, is that like saying hello? I was thinking yellow as an answer to something. I was like, what answer? Yellow is the answer, but what was the question? But okay, I get it. You're like, yellow. Is that what you're doing? Is it? Yeah. Cool. I'm going to say that you are. Otherwise, I feel like a right fool shouting, yellow, and you're like, no, I was giving you some information. Hello, Poppy. Hello. That's where you are. I love how you and Daisy are like tag teaming now. That's nice. Hello, Lewis, in Gran Canaria, being joined by his bro Thomas and sister Isabel as they love learning about space. Really? Lewis, are Thomas and Isabel still here? Because that was quite specific, wasn't it? It wasn't like, oh yeah, Mars is red. It was quite astrophysics-y. Are they okay? I hope they're okay, Lewis. You take care of them. They're not used to this. My daughter is. Oh, that's good. Oh, yeah, I see what you mean. I've put say hello in the comments if you're watching this live. And Tanya's daughter is watching this live. Oh, that's nice, Tanya's daughter, isn't it? Did Tanya just like quickly write that and then run off to do something and now it's just you and me? That's so nice. Hello. I'm just going to call you daughter. All right, Kai, hello you. Let's do a little refresh to see. Oh, also, YouTube, Facebook doesn't always show me all the comments. Apparently they were just the most relevant comments. So sorry if it didn't come up. That's just Facebook making a judgment. Okay. One quick refresh and then we'll go. Yeah, sorry, I'm really confused about whether I should set this YouTube channel to made for kids or not. Maybe I shouldn't actually. I've set it at made for kids, which means that none of my videos have comments. But actually, well, I don't know, because one of you's 8, so I probably should make it made for kids, shouldn't I? Probably should. In YouTube land, a kid is anyone under 13. So this is like, it's probably exactly 50% of you under 13. So we'll say that this video is for kids. Any more comments? No, I don't think so. It's Freya and Hannah, and now I can look at Freya's picture of a unicorn. Sorry, it was Hannah. Yeah, it was tough going at times. Sorry, you two, sorry. All right, let's have a look at Hannah's unicorn. Whoa, that, my friend, is an alicorn, am I right? I've watched enough My Little Pony to know what this is. It's an alicorn. It's got wings. Oh, do we need to do... So if you're watching if you're not watching my all ages lessons, we're doing mythical creatures at the moment. So we're getting very into dragons, unicorns. We just learned all about how someone had sex with a cloud and that made centaurs. Really, really enjoying myself. You should totally come. If you're watching live, you should come next week where we're going to get DNA out of a strawberry. It's very exciting. Right, I'm going to go. Thank you so much to the people who have signed up literally while I've been talking. This is such a cool job. It's all of the things that I love. Honestly, in my life, the things that I've loved doing most are customer service, acting, teaching and busking. And this is just like, the king of all jobs for me. So much appreciated, really. I'm going to go and start doing some more planning for next week. Thank you so much for joining me, and I'll see you very soon. Like and subscribe. Bye!